Hey folks, today I'll be talking about Cellular Automata, and this is basically the new hot take, the new medium piece that you get to hear first on some computational theories and stuff like that. This deck contains GIFs. I thought I would give you a fair warning. There's no wombats. I'm really, really, really sorry about that. But there's other GIFs. So hello, Edinburgh. Was that good? I am Irina on Twitter. Ira is the short version of my name. You can call me either or. And yes, today we're talking about genetically evolving cellular automata, or just cellular automata. And that's really, really quite confusing. What is cellular automata? Is it Latin? Is it French? Just kind of confusing. So I think a good way to start this off is just let's tell a story. Stories are great. So I'm from Vancouver. That's in Canada. It's the only warm place in Canada. It rains a lot, all the time. And so I enjoy the outdoors, and I hike really quite often. And so once upon a time, I was setting out on a hike. And it was pouring out rain, so I decided to take shelter in this library that looks like a giant coliseum. You might have seen it in Battlestar Galactica. If you're into that show, it's there. And so what they had was like this book sale where they've been selling books that are $1 or $2, which is about £1, maybe 75 pence. And so I picked up this book. Or actually, I didn't pick up this book. I picked up a really cool edition of Hitchhiker's Guide to the Galaxy. And my friend that was with me picked up this book on complexity, and he said, oh, this is a nice black cover. You should take a look at it. And so I opened up this book, and it seems really, really interesting. And so this entire journey basically starts with the book by Melanie Mitchell called Complexity, a Guided Tour. And this entire book takes on a really interesting observation about everything in our world that could or could not comprise a complex system. So it would talk about scale-free systems. It talked about entropy. It talked about everything from actual computers and things like that. And then this one little small chapter in sort of the beginning of the book talked about cellular automata, or a discrete model in computation and mathematics, which really caught my eye. And she kind of walked through the entire concept, and she talked about what it is and what could be done, and some of the models she's built with it. So I decided to get coding and see what I can come up with once I've read through some of her examples and some of her other papers. And I got to this. And I was like so excited that like I came up with these interesting ideas just by reading the book, and it was really, really interesting to me. And so yeah, let's talk about cellular automata. Let's dive into this straight with John von Neumann. And if I say Newman, it's only because I've called him Newman for a very long time, but if I say Newman, I mean Neumann. I just forget. So he was a mathematician, physician, very many things. You might have known him as somebody who's worked on the Manhattan Project, but he's also written a really interesting paper on theory of self-reproducing automata at later stages in his life. And he's talked about and that paper is basically the start to some of the interesting ideas that came out after it, and the basic idea is kind of artificial intelligence, and that stemmed from that essential paper that was published after he's been after his death. And kind of this entire thing talks about cellular automata and self-reproduction, things like that. And it's really interesting. So he describes two kinds of automata that exist in the world. And that's kind of where we'll start this journey. Two kinds of automata. So there is your artificial kind, which is computers. And there's like these natural kinds like seashells, and I think they're called symbiola shells or conus shells, and they're kind of the natural cellular automata. And today we'll be talking about the artificial kind, so computers. Computers are great. And so let's talk what they are. Let's talk about what they are. Like, what are some of their characteristics? What are some of the traits they take on? A lot of the automata is based on the kind of rules they take, or because the rules are basically what defines a particular outcome. So that's kind of one of the characteristics. But there's more or less out of some of the papers I've read, I've basically come up with 4. One is that the result is dependent on the part's definition. That's basically the rules. So whatever you come up as an outcome depends on what you've started off as a rule. Kind of similar to what we do normally in programming. It kind of has to have awareness of its parts. So I'm here, I kind of have to know what's around me. And so does this automata. So know all the things. Whenever it produces operations, it directs them at not itself, or it directs them on objects around them, kind of thing. So not directed at themselves, but on the results they produce. And it's decentralized. So more distributed of a system. And not quite a characteristic, but something that people have noticed once they started working in these things or looking into these things, is that they produce a much more complicated object from very uncomplicated parts. And this is why it's been so fascinating to so many people, is that you have something very, very simple, but you come up with something a lot more complicated. And so kind of one of the very, very first examples of these automata was actually the Turing machine. And you might have watched the film, or you might have just studied Turing machines on your own at university. But Turing machine is basically one of the first automatons. So what happens is that you have an automaton that produces the action. It's the little thing that punches the tape. So it produces an action. The tape itself is what the product is. So when the puncher punches the hole in the tape, it's directing its action of punching onto the tape, but it doesn't direct it at themselves. And what you get is, in fact, a completely different construct. So you have this automata that modifies a tape, and the tape was completely different before it got punched through with whatever is the output. And the automaton itself doesn't actually know what happens before or after it punches the tape. So it's really really cool, just really cool. And so essentially what happens is that computation emerges just from simple rules being followed. So the Turing machine, or the automata that punches the tape, knows what it's supposed to do when it gets something, and it just does it based on that particular part. Okay. So cellular automata models a natural system, and that's why it gets so many people very excited about it, is because it's a very simple model that we eventually are able to take on and produce something else. But we're trying to do this because we want to kind of model something that's a lot more complex than we're able to produce, and that's why the simple parts are so interesting to us. So let's look back at that trait number 2, so awareness. Much like in life, a lot of what you do is dependent on how you work with your neighbors and how you're friends with other human beings, because it's nice to be friends. So von Neumann, when he was writing his paper on self-reproducing automata or automaton, he kind of put that idea of neighborhoods or awareness into its process. So he initially put together a little grid. It was literally light bulbs with a bunch of sensors or a bunch of wires going around. It was light bulbs, and they were all dependent on the light bulbs around them. So I'm the central light bulb, and I'm dependent on everything that's around me. And that's really interesting, but the way they turn on and off was determined on what the neighbors have been doing. And so each would have its own function, but it's a function of its neighbors. So that was kind of the original thing. And then somebody came along in the 80s, I believe, Conway, one of the mathematicians, and he said, okay, I want to build a replica of this with computers rather than just having light bulbs and wires, because that's really hard and very difficult, and that was the 60s way of doing stuff. So what he said is that, yeah, I'm going to build the same thing, and I'll do it not using koalas. This is just my example. Do not quote Conway as koala man. So what you start off with is you being the central cell, you're a koala. And what you go on is that you're dependent on all your neighbors, and all your neighbors are turtles at the moment. And your definition is based on what your neighbors are. And in papers, they use dead or alive. So you basically can be in either of the two states. You're a koala or a turtle. In mathematics, I think they say dead or alive. I didn't like that term, so I'm using koalas and turtles. Way better. So basically, if you start off as a koala, you are the central cell, you're a koala, and you have at least three turtles around you, you become a turtle. And if you have 2 or 3 turtles around you, you stay a turtle. And if there are less than 2 of you, you become a koala. So it kind of works like that. So what happens is that you have this very large grid. You can start off with a very large grid, a very small grid. So people have been playing around with that. And they've gotten things like this to work. So on each kind of second, you would be changing different states. And glider is probably one of the kind of simpler examples, and really, really interesting, is that, yeah, you have a state of black or white, or you can still imagine this is koala and a turtle, and then you keep changing states based on who is around you. And aside from that, there's so many more, and you can kind of look through Google or Wikipedia, and there's many more interpretations. But another one that's really, really interesting is like a blaster. So this is a much larger grid. That one was, the one before was, I don't know, 6 by 6. This is going to be a way larger grid, and you still have these cells of black or white, or koala and turtles, and they change over time, and they produce like this really cool blaster, like in old school video games that I don't know the name of, but that's okay. So these are the kind of automata that are two-dimensionally, and they're binary. So you have 2 states, but you're also two-dimensional because you are dependent on all the neighbors around you as a koala. And so somebody else came along and said, okay, this is too complicated. I don't want to know what everybody around me is doing. I just want to know what the next 2 neighbors around me are doing. So a mathematician called Wolfram put together like a really giant book on elementary cellular automata. There's about 1,500 pages in that book. I've read just one of the smaller 50-page papers, which was really interesting. But he talked about a one-dimensional and binary automata. So it's also 2 states, a koala or turtle, or any other kind of 2 binary state, and 1 dimension. So you start off as a koala, and you only care about the 2 turtles next to you. And what happens is that you kind of progress over time. So let's take a little bit of a closer look with this one-dimensional automata. So you start off on a lattice. Lattice is just like an array. And you have an array of different automata, which are either koalas or turtles. And you would be dependent, as an entity, you would be dependent on your 2 next neighbors. And the lattice just kind of continues on and rolls on and on and on and on. And what happens is that as a one-dimensional lattice, you progress over time. So your state changes on kind of the next generation. So if you were a koala in one generation based on the specific rules that I've mentioned in the kind of the beginning of this talk, you would be changed into something else. So the first try with this, I just did it with jQuery and DOM elements because why not? It's awesome. So I looked at I've set up a set of divs that were basically my cells, and I said, okay, I'm me, and I have a next element sibling and a previous element sibling, and I'm going to take a look at what I am and what my neighbors are, and then I'm going to deal with it. And that's how I'm going to change kind of my own state. And then once I find out what my neighbors are, I'm just going to toggle the class. So given if I am active, I will change it to being inactive, and if I was inactive, I'll change to be inactive, just based on the kind of the rules that we follow. And in the next iteration of this, I looked into setting up kind of a more or less of an object that's going to be a lot more organized in my head, first of all. And I could probably write this as an API rather than just dealing with the DOM elements, because eventually I want to be doing a lot more with this. So I've set it up as like I have an automata, and it will consist of different lattices. Because it's a one-dimensional automata, it will be lattice after lattice after lattice as it progresses over time. And then what will happen is that my lattice will have different cells, and the cells just contain a state. And instead of kind of checking previous sibling and next sibling like I've done in jQuery, what I then want to do is have a right and a left neighbor. And I will see what they are, whether they're true or false. And what I got from that is a pretty neat pattern. And this one is actually, and I'll exit this screen, I think. Just because this is on a much larger scale, you actually can't see the patterns as much as you would like. And so given a completely random initial state, which would be the very top of this page, R, not F. You're then able to kind of get through kind of this pattern of automata. And what's really interesting, like you'll see kind of these absolutely random lines going down or going down diagonally, and this will be entirely different if I were to refresh the page, right? So it's completely different every time. So if you remember, we started off with very simple rules, and we went off to basically build a really complicated project or really complicated outcome. And this is following rule number 110, which is Wolfram came up with 2 to the power 8 of these. So I think that's 256 different sets of rules that automata could follow. And this one is supposed to be, this one is Turing complete, basically. Awesome. So we'll notice that certain patterns start to dominate in kind of this entire project. And what a pattern is, as defined by Crutchfield and Hansen in one of their papers, is a set of configurations sharing a very common spatial structure. So you were able to see kind of those triangles that keep going down. They're very sporadic, but there's also some trends going on. And what people then went on to discover is the fact that there is some sort of spatiotemporal behavior where the system organizes itself into patterns and, in fact, organizes itself into patterns. So we're not doing anything. It just follows the rules and it just does its own thing, which is, pretty exciting. And kind of tied into this entire theory of you got these items that are basically following very binary set of rules is this theory of it from bit. And I'm going to read this quote out because it's super interesting to me. It from bit, otherwise put every every particle, every field of force, even the space-time continuum itself, derives its functions, its meaning, its very existence entirely, even if in some contexts indirectly, from the apparatus elicited answers to a yes or no questions, so very binary. It from bit symbolizes the idea that every item of the physical world has at bottom, a very deep bottom in most instances, and a material source and explanation, that which we can call reality, arises in the last analysis from the posing of yes or no questions. So this entire cellular automata was based on yes or no questions. And the registering of equipment evoked responses, in short, that all things physical and information theoretic computers in origin, and that this is a participatory universe. So John Archibald Wheeler put this quote together, and I kind of like it because it's just really interesting. So spatiotemporal behavior, where the system organizes itself into patterns. Cool, and we started off with something very binary. So we're basically building a complex system, automata that produces a complex system that's more complex than itself. So what is complexity? And I think people who work on complexity are more confused than people who want to choose a JavaScript framework, because there is literally very different answers from very different people as to what complexity really is. And I kind of merged together a couple of answers that I thought fit it best. Complexity has to answer 3 different questions. How hard is it to describe whatever the problem you're facing? How hard is it to create? And what is the degree of the organization? And kind of answering those questions, you're able to determine whether or not something is complex. And basically, Melanie Mitchell puts together 2 interesting points of view on complexity too, is that something that's complex is how much is the average information content or amount of surprise you get from something that's complex. So with the cellular automata, with rule 110, we started off with something very simple and ended up with something really complex, and that was kind of a surprise. So there's that. And another definition is basically algorithmic information content. So that's a very fancy term for saying how long will your program run to generate a complete description or a complete replica of whatever you've created. And with rule number 110, it's pretty freaking difficult. So. All right, so a little bit on genetic algorithms. So I've looked into some of the ones that are on one-dimensional and binary states, and a lot of the things that people put together with these are working with density classification, synchronization tasks, and random number generators. And it's pretty kind of interesting the way it gets done. You basically run fitness tests, and you derive a set of rules from your initial starting state and kind of continue on. And a really interesting one that Crutchfield, Das, and Mitchell put together is that you start off with a set that is generated based on each generation. So generation is basically you run through 200 years, one generation, next generation is another 200 years. So your best fit ones get picked out of this entire set. So you perform a fitness level test and see which ones performed better, which ones are cool, which ones are hip. And then you sort in order of fitness, and you pick the best 20%. And then the rest of the 80%, they've kind of crossed over of the 20%, and they picked the rest 80, and they ran it again, and again, and again, and again. And it was pretty silly in generation 0, because all you got was like black dots, even though you started off with some white and black dots. And then in later generations, they put together kind of like these interesting patterns that emerge as they were trying to run these over. So I think this is generation 8, and then generation 13, and it got a little bit more triangulated in generation 80. I think they ran up to 150 generations. So it was kind of interesting with the one-dimensional ones. But where it got really interesting, and what I'm trying to work on at the moment, is working with image processing. And that requires to actually use a 2-dimensional automata. So I tried working with like the 1-dimensional ones, but nothing cool came out, even though the work with 1-dimensional ones is really cool anyway. But I was interested in image processing. So something that I started to look into was some of the papers written in image processing where they worked on the 2-dimensional lattice, so you're the koala and you care about all your neighbors around you. So then to be able to kind of produce the next object. So then what my lattice basically looks like is that I have my automata, and I have my lattice, and I have my cells, but my cells now kind of have everybody around me, and I have my state. And what some people put together, and the citations on the bottom. What some people put together, they started off with giving this automata some input. And then what just gave them is triangles, circles, and small things like that. And what they would do is run through this automata and hopefully produce something else as an output, or like exact same thing as an output once it runs through and learns. And that step between automata and output would go through an extra fitness level test and kind of see, does it compare from, how does the input and the output compare? Is there differences? Is there not? And a lot of the times it was actually pretty successful. So square would look like a square, a circle would look like a circle. A blob did not, however, look like a block, like a really misshaped one was having some trouble. So this was like a really kind of simple way to put together this two-dimensional fitness level and evolution tests. All right, I'm quite a bit over time and I apologize. There's a bunch of resources. They are biased in terms of how much I liked to read them. I might add a couple more for you to read. And thank you so much for listening. I hope you enjoyed this very computational talk. Thank you very much. And the slides are online if you are interested in hearing them. Thank you.